And it is my great pleasure to introduce Bárbara Gutiérrez. Bárbara will be talking today about effectual topological complexity. Thank you very much.
Yeah, hi everyone. First of all, I want to thank to the organizers for giving me the chance to present this talk. In this talk, I will introduce a new version of the topological complexity called effectual topological complexity. Before starting this concept, we'll see another TC version called effective topological complexity, which is closely related to Blasinski and Kaluba's effective TC. These two notions are motivated by the idea of taking advantage of symmetries in the motion planning of an autonomous system. We'll study some of their properties, and in the case of effectual TC, we'll study its behavior for spheres and surfaces. So let's start by recalling the definition of Farber's topological complexity as the sectional category of the endpoints map, where Px is the path space of a topological space X, which is path connected. So this map goes from here to X cross X. And as we know, this map takes as input a continuous curve in X and turns back the initial point of the curve and the final point of the curve. We are considering the reduced version. Then suppose that you have a topological space X and a G topological group acting on the right on X. And consider this space pkg of X, where K is an integer greater or equal than 2. Defined as follows. So pkg of X is the set of 2k minus 1 tuples whose entries are alternating elements in the path space alpha i's and elements in the group gi. And this element starts with a curve here and satisfies the following property. So the translation by gi of the final point of the ith curve agrees with the initial point of the a plus 1 curve. So we can think of an element here as in the image, a pair of curves and elements in the group that are connecting finals and initials of the curves and a final curve. Then we have this proposition telling us that this map EK from pkg of X to X cross X, given by the evaluation of the initial point of the first curve and the final point of the last curve, is a vibration. So here we have this image. So EK takes as input an element here and turns back the initial point of the first curve and the final point of the last curve. So we define the K-effective topological complexity, K-ETC, of the G space X, denoted by this symbol as the sectional category of the previous map, EK. So at this point, we can ask how this new notion is related to K's effective topological complexity, TC GK of X, defined by Blasinski and Kaluba. So before comparing these two notions, let's recall the definition of Blasinski and Kaluba's effective TC. So consider the space PGK of X that is a subset of K copies of the path space, a Cartesian product of the path space. So an element here is a K tuple of curves satisfying this property. So the orbit of the final point of the A-1 curve agrees with the orbit of the initial point of the ith curve. And then consider this map epsilon sub k, which takes as input an element here, a K tuple of curves, and turns back the initial point of the first curve and the final point of the last curve. And the effective TC of Blasinski and Kaluga is the sectional category of this vibration. We have here some properties. This property tells us that our effective TC is greater or equal than the effective TC of Kaluga and Blasinski. And if the G action on X is principal, the equality holds. This property tells us that our effective version stabilizes as K grows. In fact, it stabilizes in K equals 2. And from now on, so this symbol will be denoted just like this, the effective TC of X with respect to G. We decided to work with this version because we think it has a slightly better behavior than Blasinski and Kaluga's. For example, this space, this one, is designed to encode precise slipping information that assembles a broken path here. In particular, the projection from this space onto this one that forgets all the group coordinates gives us this inequality. On the other hand, in our case, this equality holds under no special restrictions, while Blasinski and Kaluga's requires a principal action. Here we have some other remarks. So if we consider epsilon, the map from the path space cross the group to X cross X given by this expression. So epsilon takes as input a curve and an element of the group and turns back the initial point of the curve and the translation by the element of the group of the final point. This map is a vibration, and we have that the effective TC agrees with the sectional category of the map. And another property is that the effective TC is, our effective TC is a G homotopy invariant. For a G trivial space X, we recover the standard TC. So if we have a morphism kappa between two groups, G1 and G2, with X a G2 space, then the effective TC of X with respect to G2 is less or equal than the effective TC of X with respect to G1, where the space X is seen as a G1 space via kappa. In particular, we have this inequality that our effective TC is less or equal than the standard version of the TC. Now, let's define the effectual topological complexity, ETC, of a G space X, denoted by this symbol. So the effectual topological complexity is the sectional category of this map epsilon from Px to X cross the orbit space, given by this expression. So epsilon takes a curve and turns back the initial point of the curve and the class of the final point. In this notion, we think of motion planners connecting any given state of the system with a desired final J-orbit. We have here this remark: epsilon is a vibration if and only if the projection is so. And in this case, this effectual TC is nothing but the Pavesic's topological complexity of the projection. From now on, we are mainly interested in free G spaces for which the projection is a covering projection. Now we have this proposition telling us that if we consider this diagram, so these squares are commutative, and we have here strict pullbacks. Let me. Strict pullbacks. And this map here, Q, takes as input an element here and glues the splitting curves alpha and beta through the inverse of this element of the group. So we can conclude that the sectional category of this map, which is the effective TC, is less or equal than the sectional category of this map, which is the effectual topological complexity, which in turn is less or equal than the sectional category of this map, that is the topological complexity of the orbit space. Pavesic shows that this square is a homotopy pullback whenever the projection is a vibration. So let's start with examples. Consider the n-dimensional sphere with the antipodal involution, and we know that the quotient space is the n-dimensional real projective space. And in this case, we have that the effective topological complexity equals 1. These are very easy to see. We get that the effectual topological complexity is between n and n plus 1. Let me say some words here. Using a Pavesic result, we see that the effectual TC of the sphere is greater or equal than the Lusternik-Schmirelmann category of the projective space, which is n. And in this paper, we constructed a effectual motion planner with n plus 2 local domains. So this number is less or equal than n plus 1. And this number is less is less or equal than the topological complexity of the quotient space agrees with the immersion number -1 in the parallelizable case, or just the immersion number otherwise. We know the answer in the case of the parallelizable, case, sorry. So n equals 1, 3, and 7. And in this case, the effectual TC agrees with the standard TC of the projective space equals n. We believe that these three special cases are the only ones having this behavior. In this case, we can construct optimal motion planners that for the case n equals 1 has the following description. So in our first local domain, we consider the set of all pairs x, the class of y, where the inner product of x and y is greater than 0. And in this case, it's easy to design a rule. So for each element in the circle, it's enough to visit the representant of the class satisfying this property through the geodesic arc, like in the image. Secondly, for the last local domain, using a non-zero vector field, it's possible to visit an orthogonal representant for each element in the circle, like here in the image. And this is an optimal effectual motion planner. Now we have here the effectual TC of surfaces with antipodal action. So think of the orientable surface sigma g of genus G embedded in R3 as here in the image. So that the reflection in all coordinate planes yield symmetries of sigma g. Consider the antipodal involution on sigma g. So this action changes the sign of each coordinate of every point here. So this makes sigma g into a C2 space with quotient the non-orientable surface of genus G+1. The case G equals 0 is the two-dimensional sphere for which we don't know the answer. It can be 2 or 3. The case G equals 1 is the torus. And here we found a very interesting phenomenon. We get that the effectual TC of the torus equals 3. In this case, these inequalities are strict. In the case of the torus, the effective TC equals 2, effectual TC equals 3, and the topological complexity of the Klein boron, according to Van der Broek and Cohen, equals 4. Moreover, this example, the example of the torus, this case represents a counterexample to the Pavesic's conjecture, which establishes this equality for every finitely sheeted covering projection. Because we have here that the effectual TC equals 3, which is different to the topological complexity of the torus equals 2. I will say some words about the proof of this equality, this one. So for this inequality, we consider the following computations. In this part, all cohomology groups are taken with mod 2 coefficients. So we know that the cohomology ring of the torus is generated by elements in the first group, alpha and beta. The first group equals C2 plus C2. And these elements satisfy the following relations. So the square of alpha equals the square of beta equals 0. And the product equals gamma, the generator of the second group of cohomology, which is C2. In the case of the Klein bottle, we have two generators again in the first group of cohomology, kappa and lambda. The first group is C2 plus C2, subject to the following relations. So the product of the elements is 0, and the square of the elements equals the square of the elements equal to the generator of the second group of cohomology, which is C2. Then we consider the induced map by the projection, and this map satisfies this equality. And for getting this one, we consider this element in the kernel of this map. And here we are considering the identification of the path space of the torus with the torus through the standard homotopy equivalence. So this element is in the kernel of this map, and the cube of this element is different to 0. So according to the zero cup length bound, we get this inequality. For this one, we construct an optimal effectual motion planner with 4 local domains. The idea consists of, for each element in the torus, we visit a half of the torus, including the half of the boundary and the half of the boundary, and so on. For preserving continuity, we have to do it in 4 local domains. So it's quite technical, but this is the idea. So again, we know that the effective TC of the torus, according to Natalia Aguilar and Jesus Gonzalez, equals 2. The effectual TC of the torus equals 3, and the topological complexity of the Klein bottle equals 4. So we have here additional information. For the case G greater than 1, the genus, so we don't know again the answer. It can be 3 or 4. And at this moment, we haven't been able to construct a 4 domains effectual motion planner for sigma 2, neither in this case or this case. And it might be, of course, be plausible that all numbers equal 4. Such a possibility can be explored via obstruction theory, but the explicit details would seem very, very challenging. And that's it maybe it was too fast. Yeah.
All right. All right. Thank you very much. I think we can start a round of questions. I don't know if people have questions, please feel free to ask them.
Yeah.
All right. Well, I might have just one comment rather than a question, and is the fact that the last point that Barbara mentioned, that this inequality, no, but for the previous one, the one that is just a little bit on the top, that one. The fact that we have these two inequalities somehow reflects Lucille and Dan's calculation of the Michael's obstruction for the TC of the claim ball being maximal, namely the corresponding obstruction in the case of the effectual vibration, the vibration that defines the effectual TC. That obstruction is trivial. And as a consequence, one can deduce that these Michael's fibers obstructions for responsible for the TC of the claim bottle being 4, that obstruction is a 2 torsion obstruction. It's actually killed by 2 times. So this is a kind of an interesting consequence that one can deduce just from explicit construction of an effectual motion planner, rather than describing the actual obstruction by itself, which is really, as Barbara said, it's a little bit complicated. It's too technical.
Yeah.
So I have a question, if it's okay. Going back to the pullback diagrams you had with Pavesic's TC.
Yeah.
The one on the left, that's also a pullback diagram, right?
This one?
Yeah, the left side.
Yeah.
Of that. Yeah, okay. So then that would mean that the that one on the left is also the very left is the effective, right? TC?
Yeah.
So that would mean that the effective TC would actually be the topological complexity of a map as defined by Murillo and Wu, actually. Because in a recent paper, I proved that that's actually the pullback of the product map, that it's equivalent to Murillo and Wu's. Just an interesting side note.
Okay. Okay. Thank you.
All right. I'm going to stop the recording now. But please, if you have further questions, just you can ask them.